Today, I'm going to talk about the safety challenges for Apollo OS. My name is Ning Qu. I'm currently the principal engineer in Baidu and from the Apollo team. First, give you some brief introduction about myself and also the Apollo project. I'm currently the tech lead of the CarOS team in Baidu IDG, and since 2016 actually, sorry. And CarOS basically is the goal of CarOS is to provide automotive grade infrastructure for the autonomous driving. And before that, actually, I joined Baidu in 2014 and working on the big data infrastructures. And previously, before Baidu, I worked for Google, NVIDIA, and Carnegie Mellon University. Then let's look at Apollo. Apollo is we call the open source autonomous driving platform. We have the full slogan here, open capabilities. Basically, we want to open as much as possible in the source code level and to show all the capabilities we can in autonomous driving. And we want to share the resource, not only the code, actually also the data. We share a lot of road tests, data, and also we have a big collection of scenarios for autonomous driving, and you can just use it through our simulation service. And we want to use all these things to accelerate innovation, and we want to sustain the mutual benefits between Baidu and the other parties using the Apollo. And this is the picture of Apollo 2.0. We call the simple urban road driving. Actually, we presented a similar figure back to July last year when we released Apollo 1.0. And at that time, actually, a lot of functions actually are missing in this figure. But until the end of last year for Apollo 2.0, actually, we fill all the pieces in this figure. And you have everything. We have 4 layers. So down there, we see the reference vehicle. We are using the drive-by-wire vehicle like MKZ right now, and also we have some other models in China. And on top of that is the reference hardware platform. And we are using the computing unit, right now it's an IPC actually. And also we have a couple of sensors as the sensor side, and normally you can see in most of our driving cars. And we have this kind of the black box, so it's totally for the security purpose, to record all the data. And at the open software platform level, and we have the RTOS right now is the real-time Linux kernel. And we have the runtime framework. Currently, we are providing the deeply optimized ROS version actually for our car. And on top of that, actually, we have all the modules like the map, localization, perceptions, and planning and control. And also we have HMI, actually very easy to use. And at cloud level, actually we have all kinds of the HD map data actually storing at the cloud. And we have the simulation service I just mentioned, it's open to public right now. And we have the data platform, actually you can download some of the data actually we have been collected. And also we have the security service and the OTA service. And the DualOS is a smart agent, like a smart assistant. So this picture is quite complete. And then let me show you a video actually in our 2.0 release. And so this is some very typical scenarios actually happening every day in China. We have been testing Apollo actually extensively actually in China, a lot of cities actually including Beijing and other cities. And you can see that that's why we say actually the China's road condition and edge case are really complicated and requires more advanced technology. So that comes to the safety topic actually. I think almost all of us know this tragic event actually. The accident happened on March 18th. And a woman actually died and after he was hit by the Uber's autonomous driving car. It was a really very tragic event. And in this event, actually, there's a lot of discussions after that. I mean, talking about why this could happen, actually. And suppose actually we can see a lot of things through LiDAR, no matter it's light or no matter it's day or night. But I mean, somehow it happens, and maybe it's due to the LiDAR malfunctioning, not generating the data. Or maybe it's because the perception doesn't detect the woman. Or maybe because the system doesn't generate the command, I mean, in time to issue this brake. But however, actually, we know that there's one thing actually we learn from this. The safety should be always the first priority actually for autonomous driving. So that's why actually we are talking about the safety topic actually from the OS perspective. So if we look closely, we have the Waymo actually is the top one autonomous driving company right now. And they have released a very comprehensive safety report. And in the report on the right side, you see that they classify the safety as the 5 areas: behavior safety, functional safety, crash safety, optional safety, and non-collision safety. And the functional safety, behavior safety, I explained a little bit. Behavior safety basically is your algorithm supposed to generate the correct command, I mean, for the car actually. But right after it is functional safety. So you see, I mean, how important it is. I will talk a little bit more about this topic. And also early this year, just right after CES, actually, NVIDIA released a very long news and described their own functional safety architectures, including both software, hardware, and all the pieces in it. So you see that functional safety is quite important actually in the automotive industry. So what is functional safety? Functional safety basically is the key technology for the automotive industry. And with more and more electronic units actually coming into the cars, and they actually define the driving experience. And we want to guarantee all these electronic systems are safe, and they can reliably work no matter, I mean, just in case they malfunction, maybe some hardware malfunction or software malfunction, but still the system should work reliably. So in a very short word, so basically the objective of functional safety is that we want to get the freedom of unacceptable risk of injury or damage. So that's why actually the functional safety is so important and at the system level. And if we look at what's happening, actually, what's inside in the car right now, actually, I borrowed this figure from the internet. It's called the explosion of electronic system. Basically, the current architecture is that each ADAS application has its own set of sensors and own processors. For example, like the forward collision warning, like the automatic emergency brake, and like the assisted parking. Every ADAS application has its own set of sensor and its own processor. So and they are very distributed actually across the car, across the system. And so that's how the industry has been doing all the years actually. And if we see the trending actually, this is our test. I use as example from the NVIDIA Drive PX. Actually, I think the consolidation is just happening right now. And there is a couple of reasons that we are doing the consolidation, like computation efficiency, like the complexity management, and the lower cost of the deployment. And so Actually, the consolidation is a very natural, idea for the PC market and also for the smartphone, things like that. But actually, it's really a whole new game for the automotive industry. And you see that in the Drive PS2, actually, it packed a very powerful multi-core CPU and together with the GPU in the platform and in a small form factor. Actually, for the Xavier, the next generation, it is much, much smaller and it's more powerful, actually. So that's what's happening right now. Then let's look at each layer in the autonomous driving and see what's the challenges we are facing right now. So at the hardware level, first, just like I present in the Drive PX, we have a really powerful processor like the general purpose CPU and also the general purpose GPU actually in the hardware platform. And previously, I believe most of the car have maybe a dedicated ASIC, for some algorithms and to process the data or to implement some algorithms. But right now, actually, we bring in more general purpose CPU and GPU. And also in Intel platform, you will see like a FPGA also in the picture. So it's kind of like a really heterogeneous and a really powerful computing resource. The system need to manage them very well, actually. And for the sensor part, we see that we have a bunch of sensors like LiDARs, cameras, and radars, and ultrasound, and all kinds of stuff. And actually, we have a lot of them. If you look at a lot of autonomous cars, maybe they have more than 10 cameras actually installed. And the diverse sensor side, and some of them are really data intensive. Like the LiDAR and the camera, generate a huge amount of data, all the time. We at hardware level, actually, this put a lot of pressure for the hardware, and also the software is it's under a lot of pressure, actually. And at the software level, actually, I first mentioned about this algorithm. So people are using the AI all the time, using the deep learning network, and it's very computation intensive. Also, I'm very glad actually the Professor Hazer mentioned about this error detection using the AI. Actually, I'm just back from the talk this morning, actually from GTC. And there's one session talking about anomaly detection on canvas. And they are using RNN, they are building an RNN model, to do the anomaly detection even on the canvas. Just happening. We use a lot of probably the deep learning models for the perception right now. But I think it's happening for a lot of things actually across this autonomous driving. It's not just perception. And we want to use the deep learning not just improve the accuracy, also we want to keep learning, during the driving. So I think it's definitely, we will use more AI algorithms in the system. And for the software system part, actually I put the 4 circles here. So as mentioned, we have a huge amount of data generated by the sensor side. So the high throughput is definitely the requirement actually for the platform to handle. And also, because the autonomous driving is really safety critical, and assuming if you drive a car on the highway with 100 kilometers per hour, basically it means that you traveled like 30 meters per second. And so if you can't finish, your processing and generate the command in right time, in time and at the right time, basically, you are missing a couple of meters just pretty easily, and it's very, very dangerous. So high performance, real time is definitely the requirement for the platform part. And also the high reliability, because your car running for hours and hours, and you are handling all this data, and you probably have a very long pipeline through the sensor data until you send the command to the control. So you want to ensure the reliability of your system all the time. So this is really a strong requirement as well. Then the next two is the reliability. I think we are all familiar with the level 2 ADAS, for example, like the Tesla. The Tesla is, we call it, it's not really the fully autonomous driving because, I mean, the human has to monitor the environment all the time. It's not free from the driving. For the L4 and L5, actually, there's no driver at all. The human has been removed from the driver's seat. There's only passenger in the car. So for that purpose, actually, so the autonomous driving system has to guarantee the safety of the vehicle all the time. And this raises really the higher bar, actually, for the safety goal of the system. Instead of just like for the L2 or maybe L3 is easier, there's still a human driver. I mean, you can give them some time frames for them to respond. But for the L4, L5, it's totally responsible. Liability is totally for the auto driving system. So I think that's a totally different story. And as we know, actually, a lot of companies, I mean, are working on the functionality for the autonomous driving right now. But so far, I think the safety is really, I mean, should be, I mean, on the table right now. And because, I mean, no matter, I mean, you are doing the production or you doing a road test, I mean, it's really, really dangerous without the safety in mind. So how to do this? I think there is a quite good solution right now, I mean, for the current car, actually. So we called the ISO 26262 standard. This standard actually is designed for the functional safety and including like defining the system safety goal and how to design the system and also the development process and also the testing and production and deployment. Everything has been included. And at the software level and hardware level, actually, there's a chipset, I mean, meet the we call it the ACO, the Automotive Safety Integrity level, and up to the ACOD, that's the highest level. So the hardware provide kind of the ACOB chipset, ACOD chipset. And at software level, we have the AutoSAR actually has been deployed in a lot of modern cars right now. And AutoSAR is kind of quite simple and quite reliable, I mean, designed according to this standard ISO 26262. But somehow for the L4 and L5, actually, we don't see a mature standard and we don't see a commercialized solution yet. And why they need a new standard? I mean, because I mean, I just mentioned the complexity of the software system and hardware system is totally, I mean, different from what we have in the current car. So it's just way too complex, I mean, for the ISO 26262 to handle right now. So they are defining the new standard, and also the industry is proposing a whole new software stack they called the Adaptive AutoSAR. And they renamed the previous AutoSAR as the Classic AutoSAR. And in the figure, actually, I also bought the figure. It's not the exact view from every company, but actually it represents what they are thinking right now. So in this picture on the right side, basically you see that they're still keeping the Classic AutoSAR on the safety partition. And the Adaptive AutoSAR basically is kind of like a complement to the Classic AutoSAR. It's not a replacement. And in the performance partition, we have the more powerful cores. And they are even adding like the hypervisor and the OS, and on top of that is the AutoSAR, Adaptive AutoSAR stack. And so they can supposed to support more complicated applications running on top of it. So I think that's good to have. But I think, but still, I mean, Adaptive AutoSAR is also on the way, actually. They have been making a plan to make 2 releases every year since 2017 last year. So basically, I mean, the final product hasn't been ready yet. And if you look closely, I mean, in this stack, I mean, they are talking about the OS actually in the stack instead of the AutoSAR safety OS in the Classic AutoSAR stack. In the Classic AutoSAR, I mean, they provide their own OS called the real-time, very simple OS. I mean, they guarantee a lot of things. But in this Adaptive AutoSAR, actually, you see there's more flexibility actually in the OS part. I mean, they are talking about what kind of OS actually we can use in this area. So let's move to the reliable OS, actually. I'm very appreciate, actually, the Professor Hazer's talk. So basically, roughly, if you want to talk about the OS, there's two classic OS. One is the monolithic OS, and the other one is the microkernel OS. And monolithic OS is the Linux is a very good example. And they put every functionality into the kernel mode and the application on top of it in the user mode. And for the microkernel, actually, they try to, put as less as possible in the kernel mode, like the basic infrastructure, basic facilities, IPC, virtual memory, things like that. And they try to, put a lot of OS functionalities actually on the user mode as an application. For example, like the file system or like device drivers all can run in the application in the user mode. So I put three measurement, to evaluate, which one is better which for the autonomous driving right now. So basically, it's simple. Simple is very easy to understand. Actually, the Professor Hazer has been explained very well. The microkernel is just much simpler actually than the monolithic, the Linux kernel, and it's possible actually to verify it. I'm not saying every microkernel can be verified, but I'm saying that with this much smaller size form factor, actually, it is possible we can do a verification or maybe even a formal verification at this level. And also the simple means that since we have so many basic facilities, so little basic facilities inside the kernel mode, so that means that the kernel can keep more stable for the long term compared to the monolithic kernel. Like Linux, we keep adding the functionalities into the kernel, and there's no easy ways, to isolate all these functions just out of the picture. So that's really good thing, I think. You keep the kernel as stable as possible, and you build on top of it all kinds of drivers, and that doesn't hurt your verification process, and ensure that you have a really solid foundation. And the next to it is the high performance I mentioned. Because we are handling all this data, and we have all these computation intensive jobs. And also, one thing is that we have I just also mentioned, we have the heterogeneous hardware resource. Microkernel has never really been widely used for the general computing scenarios. It doesn't really perform, as good as the monolithic kernel like Linux. Using the GPU, we have the CUDA stack, and maybe we have the OpenCL, all kinds of things. But microkernel doesn't have it. So also, the professor mentioned that the IPC, the overhead, people always express their concern about the IPC communication between those basic modules that will hurt performance anyway. So that's really, like Linux may be a better choice for this one. But we are also seeing that some microkernel solutions are really, doing some different things in this area. Maybe, pretty soon they will be able to catch up. But right now, I'm seeing the high performance part, the Linux kernel may be a better choice. And also in the previous figure, they also listed the POSIX OS. I don't think it's a hard requirement actually for the OS part. Because if you have a stable autonomous driving system, probably you can port it to any OS you like. There will be like a big efforts, depends on the API, the difference. But I think it's doable. But on the other way, if we say that it's waste a lot of time and engineering people, to do this. If we can provide a microkernel with the POSIX API, it will simplify a lot of people's work. It doesn't mean that you port your application just to this microkernel, you can run it. But you provide the compatible API, you kind of simplify a lot of work, before you're debugging your system on this new operating system. So, yeah, so it's not like the answer for the OS part, but I think the microkernel is really having a lot of advantage in this automotive area compared to Linux. Yeah, that's basically concludes my talk today. And so we have the Apollo 2.0 right now available on apollo.auto. And also we have the GitHub repo, github.com Apollo Auto available as well. So actually, I hope you guys actually watch the updates from our Apollo project. We will have many exciting and interesting things released pretty soon this year. And yeah, I just need to mention that we are hiring, and we are welcome everyone to join the Apollo project. Thank you.